So let's look at our first sorting algorithm. Now, just so you know, if you feel like you want to know more details about any particular sorting algorithm, I highly recommend checking out that sorting algorithm on Wikipedia. Wikipedia is a fantastic source for these sorting algorithms. All right, the first one we are going to learn is selection sort, because what we are going to do in this one is continuously find the smallest item, select the smallest item, and swap it into the appropriate place. Okay, so let's go ahead and scramble this up and see how that works. Okay, I think this is fairly good. Okay, so the first thing we are going to do is that we're going to go through. Is this the smallest thing I've seen so far? Well, yes it is. What about this one? We're going to go left to right and find the smallest thing we found so far, right? What about this one? Is this the biggest thing, smallest thing I've found so far? Yep. This one, no, 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 no. This is smaller than all of them as I go through, right? We're going left to right. This was the smallest thing, so what I do is that I swap this with the item that's currently at index 0. Boom. Okay, so we found the smallest item in the list. We selected it and we swapped it into index 0. Now we're going to find the smallest item of the remaining things and swap it into index 1. You may recognize this from your first timed lab if you took a timed lab, right? So here, we now need to go through and select the smallest item. This is so far the smallest. Well, that's smaller than that, but that's smaller. And so this has got to be the smallest item so far in this subset. So we're going to go ahead and swap this into index 1. Now I'm going to move these guys out of here just so that they're off to the side. These guys are kind of locked into place. There's the first, it's the smallest, and the second smallest. We don't really have to consider them anymore. Okay, now let's look at all of these. Okay, is this the smallest? Yes, it is so far. And we go through and we find out that this guy over here, that's the smallest. So we're going to go ahead and swap them into index 2. What about these over here? Well, this is the smallest so far. Swap with this. So if this is the smallest, so we swap this into index 3. Smallest, smallest, smallest. Right, we've successfully find that each one is smaller. So we're going to swap this into place into index 4. Okay. Now we get into an interesting position over here with the remaining 2. This is the smallest item this is the smallest item, right? So for index 5, we swap with the smallest thing with what's ever in index 5, which means we kind of just swap it with itself, right? Don't blame me, blame the algorithm, right? But we swap whatever's in the item we're trying, whatever is in the location we're swapping into with the item with the smallest item. They happen to be the same thing. So, go figure. And then for the last item, well, the last item is going to be the biggest item, so we really don't have to do anything with it, except not drop it, right? So we are done, right? So that is selection sort in a nutshell. All right, and what's interesting? So let's go ahead and evaluate this. How many comparisons do we really have to make, right? So for the first, we have 7 items here. So we had to look at 1. So for the first finding the smallest item, we had to do 7 comparisons. Then we had to do 6, then 5, then 4, then 3, then 2. And then the last one, we just kind of said, hey, it's the biggest, we're done. Okay, so that was 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, right? That classic scenario. So that's O of n squared, right? Kind of hand-waving it there a bit, but you see what I'm getting at, is the point. So that is, it has O of n squared comparisons. But as we went through, how many times did we have to swap an item, right? Consider it out of order again, right? We'd go through once, we'd find the smallest item, and then we'd swap that. And then we'd go through, and we'd find the smallest item, and then we'd swap that again, right? Then we'd go through, and we'd find the smallest item, and we'd swap that again. We'd go through, we'd find the smallest item, and we'd swap. So every time we find the smallest item, which takes O of n time, it takes O of n time to find the smallest item out of the remaining n items, right? Well, it's going to get smaller and smaller. Being a bit loose with the terminology there, but every time we go through and we find one of those items, it takes only 1 step to swap. So the important thing to realize about this is that swaps are generally much, much, much cheaper than comparisons, and comparisons are much, much more expensive. So we really only care about experiments in most cases. But say, for the sake of arguments, for some reason, the comparisons are super, super cheap, right? So much so that they don't really count, In that case, you want an algorithm that's very, very, very effective in the terms of how many exchanges or swaps it's going to do. And if you want to minimize the number of swaps, selection sort is your sorting algorithm to call, right? However, it's O of n squared, and it's always O of n squared, right? What if we passed in the sort in something that was sorted, right? Watch what happens here. This is a sorted list, right? So we find the smallest item, go through all of them. Oh, and we sort it with it, and we swap it with itself. Go through all. So now we go through, we check all of them. We find that this guy's the smallest, so we swap it with index 1. Go through all of them again, even though we can plainly see it's all sorted, right? So it's going to take O of n squared time even if this thing is sorted, right? Or even if only one thing is unsorted, right? So it's always going to be O of n squared, which kind of makes it our worst algorithm of the batch we're going to learn, but hey, at least it's consistent.